Hello, Earth Science students. Welcome to week 4. In week 4, we are going to start our journey through geology part of our course. So I'm going to start with Earth's evolution through geologic time. This is chapter 12, and I'm going to start saying this a lot, basically every week, but please make sure to read the text. I am taking my lecture format from a previous course that I have taught, and so my lecture is set up a bit differently than the textbook. I cover some things differently than what the textbook does, so do make sure you read your textbook. So before we start going through our planet, we've talked about all of the planets in our solar system a little bit. Why is it that we on Earth have life and we don't really see that on the other planets? Well, our planet happens to fall in what is called the habitable zone. So the habitable zone is basically the happy place in a solar system where you have liquid water. There's a lot dependent on the distance to the sun. You can't be too close to the sun because if you're too close to the sun, it's too hot. You can't be too far away from the sun, or star rather, because it'll be too cold. So you want to be in that happy zone in between. You need to have an atmosphere. So again, tend not to have strong atmospheres close to the sun, but too far away, you may have too heavy of a gas atmosphere. Liquid water, again, is very much tied to the distance to the sun. Topography is also important, so we need to have some variation in the landscape that can allow different things to develop. So if you have a uniform planet, you're not going to basically have the ability for diversification. And then finally, time. You don't see things developing right away. So a planet needs to be mature for life to have evolved. And we're going to see that today, that life didn't spring up right away on our planet, and it took a long time to get to the point where we are now. So, how does Earth become Earth? We start off with the Big Bang about 13.8 billion years ago. This is when we had hydrogen and helium atoms first being created, and those would then become the building blocks for the rest of the universe. Our particular galaxy, the Milky Way, forms about 10 billion years ago. So it's not the earliest galaxy, not the youngest galaxy either. During the formations of the galaxies, heavy elements were synthesized by those supernova explosions. So those larger mass stars, when they die, they produce some of these heavier elements which are necessary for the full chemistry of our planet. Our particular solar nebula began to contract about 4.7 billion years ago. This then led to the disk. So as the material collected to form our protosun, rotation from gravity pulling in started to form a disk. It flattened out the nebula. As things started flattening out, they started having more collisions and we had materials cooling down. So we start to have accretion or buildup of the planetesimals. This is happening about 4.6 billion years ago. So we start to have early protoplanets. During this time, we have bombardment and decay of radioactive elements hitting our planetesimal, and this is going to produce a magma ocean. So we didn't have actual land. The surface of the Earth was molten. As that molten surface continues to spin, we had a process called chemical differentiation. So that meant the more dense elements were attracted to the center of the planet, and we segregated out different chemical layers to lead to the layered structure that we will be observing when we get to the interior structure of the Earth in a few weeks. Around 4.5 billion years ago, there was a Mars-sized impactor that hit the young Earth. This ejected a lot of material, also broke up the impactor. This material collected into an orbit around the Earth as debris, and eventually this material then coalesced into our moon, which is why our moon is abnormally large for an inner planet moon. And after, this process finished and we had our planet is still cooling, We had volcanic eruptions, which led to additional outgassing, and this produced primitive atmosphere. It's not the same as the atmosphere we have now. That will have to develop over time. And our oceans started being produced. And we're going to see that our oceans formed fairly early in the history of our planet. The continents, the land surface came a little bit later. So that is a very quick journey through the birth of the Earth. But again, for life to be present, we have to have a few things. An atmosphere is very necessary. So our early atmosphere did not look like our current atmosphere. Our early atmosphere was hydrogen, helium, methane, ammonia, carbon dioxide, and water. Currently, our atmosphere only holds about two of those. We have carbon dioxide and water in our atmosphere now. We don't see these other gases at nearly the degree they were in the early Earth. So the light gases eventually escaped from gravity. Gravity wasn't able to pull them in. And then we had changes in the atmosphere due to outgassing of volcanic eruptions, and that enriched our atmosphere in certain elements, which would then allow our atmosphere to develop into more of what we recognize today. In order for life to be present, we have, at least life as we recognize it, we have to have oxygen. But oxygen as O2, which is the oxygen that we breathe, was not present for 2 billion years in Earth's history, for the first 2 billion years. Around 3.5 billion years ago, photosynthesis begins. That's the process where plants take in carbon dioxide and release oxygen. Between 2 and 3.5 billion years age, we see what are known as banded iron formations. So these are rock formations that have a significant amount of rust in them, because when iron and oxygen meet, they produce rust. And so we know that there was abundant oxygen during this time period because we see these rocks that have rust that was developed during this time period. Around 2.3 billion years ago, we have what we call the Great Oxidation Event, and this is when we had this massive influx of oxygen, and we actually saw the development of ozone, O3, at this time. And ozone is very important for our planet to be habitable. Another component that's necessary for life are oceans. So oceans develop when the planet cools enough for water vapor to start to condense down to have liquid water. Because remember, that early atmosphere did have H2O, it had water vapor. So once the planet cooled enough that that water vapor could condense out of the atmosphere, we started having water collecting. By about 4 billion years ago, 90% of the current seawater was in early ocean basins. So the oceans developed very early in the planet's history. The salinity increased rapidly in these early oceans, and it remained fairly consistent for, we've had fairly consistent salinity for about 2 billion years. There are alterations in oceanic salinity with, various conditions, but overall we've been in the range of the current ocean salinity for about 2 billion years. The oceans are extremely important because they are a factory for life. We are going to see that all early life is in the oceans, and everything starts in the oceans and then moves to the land. So for today, we are really going to take an abbreviated look at Earth's history. There are different ways to look at the planet's history throughout geologic time. We have a tendency to try to put these on various visuals. During week 1, I showed you the calendar, condensing it all down to a calendar, and we don't start to see life until the second half of the year, really. This is looking at the spiral. When we look at the spiral, this period here is when we have what's called the Cambrian explosion. So probably in your conception of planetary history or Earth history, you are most likely thinking of this as like all of Earth history. And this is actually a little bit more than half of 500 million years. The majority, 4 billion years of Earth's history, there's not a lot of fossils, there's not a lot of stuff. Things are happening, but there's not a lot of evidence of it. So geologic time is a concept of this very long time period, and this is what's called a geologic time scale. So we have these different names. So we have what are called eras, and we also have what's called a super era, which would be you know, multiple eras shoved together. The eras are broken down into periods. The periods can then be broken down into epochs, and that you can actually break them down even more. The interesting thing about these charts is that typically, and when you look at the one in the upper class or in front of the classroom, it actually starts down here. That's the bottom, and they've got a little arrow saying, you know, greater than 540 million years ago or greater than 570 million years ago. So this Precambrian here, this chart is trying to show you on this side over here just how much time is being taken up by this pink section. This is 4 billion years of Earth's history. But we don't have a lot of stuff from this time period. We have some rocks. We don't have a lot of fossils. There was a period of time where we thought there was no life during this time period. It turns out there was life during this time period. But it's always interesting to look at these time scales because the majority of the planet's history is just kind of shoved at the bottom and typically ignored. So we call this Precambrian time. Pre meaning before, Cambrian is one of those periods. So we break Precambrian time into 3 eons. So you can think about Precambrian as a super eon, but there are 3 specific eons in the Precambrian. So Precambrian is an informal term that's been used since the 19th century. This is about 88% of geologic time, but we only have about 20% of our rock exposures come from this time period. So we have very little evidence left from this time period. Most of those rocks are in places called cratons. So these are the old rocks at the center of continents. These are the rocks that have been there for a long time. They're very stable. So you can find some of these really old rocks like in the middle of Canada. So we recognize 3 eons. So the oldest one is called the Hadean. From Hades for the underworld because it was not a pleasant time. This is basically as the Earth is forming. The time periods you will see on here vary sometimes. There is, you might see that sometimes it's saying 4.6 to 3.8 billion years. Sometimes it's 4.6 to 4 billion years. So don't be alarmed if you see that the time periods for especially these older eons may fluctuate between sources. GA stands for giga-annum. So giga is billion. Annum is year before present, so it's billion years before present or billion years ago. We can also have big M, A, which would be million years ago for mega. So we see that down here. So the Hadean was followed by the Archean, which is from Greek for origin. And then the Archean is followed by the Proterozoic. So Proterozoic, zoic refers to life or living being. Proto is either before or earlier. So Proterozoic was named because this is when we thought the first life was found. Turns out there is life earlier than the Proterozoic. So sometimes these names they don't change the names, but they no longer make as much sense because the reason for the name changes. The months are kind of like that too, if you think about it. October is the 10th month, but octo refers to 8 because they added 2 more months in there. So September, same thing. So sometimes these things happen. I also do want to point out that in addition to just we have very few of these rocks left from Precambrian time. This is 88% of geologic time, It's only about an eighth, maybe, of this column if we look at this column over here. Um, but this is, so these columns are never to scale. And there are very, very few exposures of these rocks. They've been exposed to the elements for billions of years. Things wear away. Things get broken down. Things don't survive. The oceans from this time period are long gone. And we'll talk about that when we talk about plate tectonics. But these poor rocks have been through a lot. So they can be hard to work with because it is, the more messed up a rock is, the more it's been through, the more mangled it gets. It's harder to find out its story. But there are rocks out there. It's just they're not as common as younger rocks. So here's another way of looking at Precambrian. This is looking at now on a ribbon. So here we have some of the big things. So we have now the Precambrian, and then we have what's called the Phanerozoic, which is our eon. It's 12% of Earth's history, the most recent 12%. Phanerozoic means visible life. So if I go back to here, the Phanerozoic is, here we see Phanerozoic would be eon, and then Proterozoic, Archean, and Hadean are also eons, and then Precambrian would be a super eon. So this has some of those big events on here as well. So about 4.5 billion years ago, the moon forms. Our oldest continental rocks are about 4 billion years old. We start seeing evidence of water about 3.8 billion years ago. We have some primitive fossils of bacteria in the Archean, so that's 3.5 billion years ago. We see oxygen coming in, 2.3 to 2.7 billion years ago. We start to see the continents forming towards the end of the Archean. The Proterozoic, we start to see some more complicated life coming in. And then at the end of the Proterozoic, at the beginning of what's called the Cambrian, we have the explosion of life about 540 million years ago. And that's why Cambrian is such an important time period. And we talk about things before the Cambrian. It's basically life and then before life, even though there was life before life. But explosion of life. We talk about the Cambrian explosion. And then again, most of the stuff that you hear about happens in this very short time period of the past 540 million years. So let's talk about some of that early stuff and then talk about some of the later stuff. So the Hadean. The Hadean eon is the time between the formation of the Earth, about 4.54 billion years ago, and either 4 billion years ago, some say up to 3.8 billion years ago. It began with the formation of Earth by planetesimal accretion. Earth was heated by impacts and radioactive decay, which is breakdown of some of those elements that are unstable. And it was hot enough to partially melt by about 4.5 billion years ago. This molten Earth underwent chemical differentiation as gravity pulled molten iron into the center. And so then we had the segregation of our different chemical layers. And outside that molten iron, we had an ultramafic mantle as an outer shell, which would then develop into some of our interior rocks. So we had some big impacts, big events. So about 4.53 billion years ago, we had the formation of the moon due to a large impact. About 4.4 billion years ago, we had our first liquid ocean and continents starting to form. Possibly the start of plate tectonics about 4 billion years ago. It's still a bit debated on when it started. But so during this time, we are going to see that the surface is largely molten. We had a loss of heat to space that would allow patches of solid ultramafic crust to form. And impacts at this time would have been very frequent. When the Earth's surface fell below the boiling point of water, water from the atmosphere would start to rain down the surface, and it would start to form those early ocean basins. So the Hadean, we're starting to form those oceans. As we move into the Archean, now we're going to start forming more of the crust. So in the late Archean, island arcs and hotspot volcanoes built small blocks of crust. Um, Breaking apart of these blocks would have produced more outpouring of volcanic material, and erosion of the blocks would produce sediment. These blocks would have been more buoyant, and so they would have stayed at the surface, and they would have collided and sutured together, which would have formed protocontinents. We would have produced other igneous rocks, volcanic rocks, by melting at depth. Eventually, throughout the Archean, our crust is cooling and stabilizing, and these early protocontinents would continue to collide and merge, and they would eventually become what are called cratons, which are the stable center to our current continents. As time progresses, the area of the Earth covered by continental crust would increase. Most of the crust had formed by the beginning of the Proterozoic. So if we look at this chart down here, crust started forming throughout the Archean and continued to form. So by the time we moved into the Proterozoic, we would have had maybe 75% or so of our, actually 80%, sorry, we would have had about 80% of our crust, and then throughout the Proterozoic, we basically formed the rest of our crust. And we'll talk more about how crust forms. This is what's called the Wilson cycle. I will talk about the Wilson cycle when I talk about plate tectonics, but it's this idea of you have continental crust that will collide and then break apart and form an ocean, and then it will, the crust will eventually, or the continents will eventually come back together to form supercontinents. So we go through these phases of many small continents that will then collide up to have few large continents that will then break up to become many small continents again, and we call that the Wilson cycle. Other things that we see during the Archean, we have traces of fossil life as old as 4 billion years. That's pretty old. So this fossil life we have is bacteria, basically. It's very simple bacteria. So we actually see signatures in our carbon isotopes that indicate photosynthesis around 3.5 billion years ago. So once we have photosynthesis, that means we can start to have oxygen in our environment. And photosynthesis is coming from more complex plant life. So we see what are called stromatolites around 3.45 billion years ago. These are bacterial colonies. So these squiggly lines are the stromatolites. So we see these in fossils. You actually can see this a lot of times in different rocks. I have stromatolites as fossils in all of my windowsills, actually. They're a very common fossil. So they're the little squiggly things. This next slide is showing us what one of these bacterial colonies looks like today. So this is a modern stromatolite from Australia. So these are bacterial mats of this cyanobacteria. These are single-celled. They don't have a nucleus or mitochondria, but they can perform photosynthesis. So it's more complex than the first life because they can perform that photosynthesis, but we're still not at multicellular life. So in the Archean, we now have oceans, we have some of our continents, and we have very basic life. Now we're going to move into the Proterozoic. So first or early Zoic is life. This was named before we realized there was life in the Archean. So this is the time between 2.5 and about billion years ago and about 540 million years ago. So what the world that would have been extremely unfamiliar to us, the Archean world, starts to transition into an Earth that's somewhat recognizable as the one we currently know. This lasted about 2 billion years. The Proterozoic is almost half of Earth history. During this time period, we had fewer larger lithospheric tectonic plates, and our continents were larger and fewer. And this is when we start to see an oxygenated atmosphere. And this oxygenated atmosphere is what we're going to see change the world. So we have these things called banded banded iron formations, BIFs. I have a very hard time saying that word. These are oceanic deposits of oxidized iron. They're very common from this time period. We do not see these being produced today. So this bright red color is oxidized iron. So we start to see that the atmospheric oxygen skyrocketed between 2.4 and 2.2 billion years ago as a result of the cyanobacteria, those stromatolites. These are algae. Evidence of this oxygen buildup is seen in these large deposits of oxidized material. They're red because it's oxidized iron. These occurred worldwide during this time, and we actually use this as a major source of iron ore today. So we also, in addition to the banded iron formations, we see a little bit later things called continental red beds. So these are now depositional rocks, so they are rocks that formed by particles settling out. The oldest ones are about 2 billion years ago. So basically these are formed from either oxidized material that was deposited, so material from these type of formations broke up and then was deposited, or material that had been deposited was later oxidized. Both of these processes take time, so we wouldn't expect to see them as early as the banded iron formations. But another indication that we had this massive buildup of oxygen, we had excessive oxygen. So we call this the Great Oxidation Event. It occurred between 2.2 and 2.45 billion years ago. The probable causes were increasing photosynthesis due to these bacteria. It saturated oxygen chemical sinks, so basically anything that could take in oxygen was full of oxygen. And because they couldn't take in any more oxygen, that allowed free oxygen to build up in the atmosphere. So suddenly we have oxygen as oxygen in our atmosphere. The effects of this buildup is that we are now going to have a formation of marine nitrates. These would have nourished some of this algae, which would give them an evolutionary advantage over cyanobacteria. So cyanobacteria had been the predominant plant life. Now, because they overproduced oxygen, because this oxygen is coming from the cyanobacteria, right? Because they overproduce this oxygen, now they are evolutionarily disadvantaged by their overproduction of oxygen. It's going to lead the way for more multicellular animals. So this increased oxygen is going to favor an evolutionary expansion of more complex life. So basically the cyanobacteria kind of, by overproducing oxygen, they led the way to no longer being the predominant life form on the planet. During the Proterozoic, we had many things happening because it was 2 billion years. Some of the interesting things that happened during this time, we had two different periods of what are called snowball Earths. One at about 2.4 billion years ago, so that was, towards the beginning of the Proterozoic, and then one about 650 million years ago, which was towards the end. So this is going to lead to a increase in different fauna, so different animal life. We are going to see the assembly and break up of supercontinents, and this is going to be in conjunction with global cooling, which could lead to the snowball Earth. So a snowball Earth happens when you start to develop ice, and that ice has what's referred to as high albedo, so it reflects a lot of the incoming solar energy. Because it reflects that solar energy, it drops the temperature, which can then lead to more formation of ice, which can reflect more of the solar energy, which can drop the temperature, so on and so forth, until you basically have ice and snow covering the majority of the Earth. It becomes a big snowball. This is called a positive feedback loop. That by having this action, it causes the action to go further and further. It's also called a runaway loop. Once this loop gets broken, that we start to melt the snow and the ice, we can actually then go in the opposite direction. Then once you start exposing dark material that will attract and absorb more of the solar radiation, you start melting it, which exposes more of the underlying dark materials, and so you can go in the opposite direction as well. We did see life diversifying rapidly after snowball conditions waned. So once the snowball finished, we saw life becoming much more diverse. So this is some of that diverse first life. So these are late Proterozoic animals. So the first animal-like organisms were very similar to modern amoeba. So we're looking at about 750 million years ago. The oldest fossils of multicellular animals are about 580 million years ago. So these are still these are more complex, that we have multicellular, they're bilaterally symmetrical, but they're still fairly simple, but we're going to see life keeps getting more and more complex. And as we move through the late Proterozoic, we see life starting to diversify. So the last 500 million years of the Proterozoic witnessed a gigantic leap in biological complexity. Simple organisms gave way to complex ones. The early life was very soft-bodied, multicellular invertebrates resembling worms and jellyfish. They appear in the fossil record at the end of the Proterozoic. I'm not going to try to pronounce this word. My tongue won't do that word. But here's that that animal life that we see. So these are different fossils. These are all impression fossils. These particular ones are from Australia, but they do occur globally. So the Proterozoic is when we started to see life becoming more diverse. It's all still in the oceans, and the Proterozoic is the end of the Precambrian time. So the Phanerozoic eon is the next eon. The Phanerozoic is composed of 3 eras. So Phanerozoic refers to visible life. It's called that because now we have an abundance of life. We see fossils. So the 3 eras are Paleozoic, which refers to ancient life, Mesozoic, which refers to middle life, and Cenozoic, which refers to recent life. We are in the Cenozoic era. It's the most recent, so the Phanerozoic is the most recent 541 million years of Earth's history. It began with the first hard shell organisms, which greatly increased fossil preservation. These hard parts made a more complete archive of past life possible. So this is what the oceans would have looked like in the Cambrian and the Ordovician type periods. So the Paleozoic era is marked by the first true fossil record, or conspicuous fossil record. So the Neoproterozoic life was largely soft-bodied. So the life we saw before the Phanerozoic, the Precambrian life, is soft-bodied. It's hard to preserve soft materials. Early Paleozoic animals, so that's the first era within the Phanerozoic, they started to build mineral skeletons, which are much easier to preserve. This life was largely confined to the marine environments. For the first epochs, it was entirely in the marine environments, and slowly we moved onto land. The Cambrian period was when we started to see a massive explosion of new species. So each of these periods, I'm sorry, I said epoch earlier and it wasn't epoch, it was period. So each of these periods is broken into early, middle, late. That's just, they can be broken into smaller epochs, but typically we describe the older periods in that way if we need to. So the Cambrian is the first period of the Paleozoic. The Cambrian is important because we call it the Cambrian explosion. This is when we have vertebrates and we start to have a vast diversification of life. We see a huge record because these hard parts are able to be preserved. So we see a fossil record. So this image in the back is Cambrian rocks that show us different species. We're seeing good preservation of them. These are all going to be in the oceans. So following the Cambrian was the Ordovician period. So the Ordovician saw the first vertebrates, which were jawless fish. We see crinoids, we see algae, primitive land plants, And at the end of the Ordovician, we saw mass extinction. So during these times, we saw the seas roiling with diverse life. We had trilobites, brachiopods, crinoids, gastropods, cephalopods, corals, sponges. The land was pretty barren. So the Ordovician, we're starting to see reefs. These are starting to, we're seeing that the oceans are this factory of life. So we're seeing all of these, these are the fossils. This is what they would have looked like in life. The Ordovician period is when we actually saw plants start to moving onto the land. So during the Cambrian, everything was in the oceans. All life was in the oceans. Around 470 million years ago, we see plants move onto the land surface. So for the first 3.5 billion years, all life on Earth was marine. So the land plants, these early land plants are non-vascular and they're related to mosses. So these are fairly simple plants. Again, we always start simple and get more complex. Not too surprising, insects followed plants on land. They evolved from crustaceans. And at the end of the Ordovician, we start to see a mass extinction. So this chart is showing us the periods at the top. So Cambrian, Ordovician, Silurian, Devonian, yada, yada, yada. Time at the bottom. We have the percent marine animal genera. So genus is the grouping between species and family. So it's species that are closely related, but they're below the family. So we're looking at here the number of marine genera, so groups. At the end of the Ordovician, about 50% of marine genera, so that's these larger groups, and 85% of marine species die off. This is probably due to glaciation causing loss of habitat from falling sea levels, because remember, we're talking the marine. But basically what we see is that at the end of the Ordovician, we have this drastic drop in the number of species. And if you look at this chart, we see these drastic drops at various times. And if we go upwards, we see that typically these drastic drops correspond with a change in period. Some of these are labeled. The reason, honestly, is that the geologic time scale, which is what this top part is, those distinctions are built off of fossils. So when we start to see a sudden change in the fossil assemblage, that we see species disappearing and new species coming, well, that's a good place to put a bookmarker on a period. So these periods are basically built off of the fossil record. And so when we see this drastic change in the fossils present, that's when we typically will change to a new period. So that's why we typically see these massive die-offs at the end of geologic periods. So at the end of the Ordovician, we have our first, not our first, but we have a large die-off. We move into the Devonian, we move into the Silurian, then the Devonian. In the Silurian and the Devonian, we see fish diversifying rapidly, and they will soon follow plants and insects onto the land about 375 million years ago. This is an example of a fish that had lungs and wrist bones. So it has these, its fins have been evolving that it can move onto land. So this is one of the first animals that actually walked on land. During the Devonian, we also start to see an evolution in plants. So instead of just being these mosses, we see a development of spore plants. We see ferns. These are developing the more humid habitats. We see seeds appearing. This is a major evolution in plants. Conifers are moving into drier habitats. So we start to see the land surface starts looking more like a modern Earth. During the Silurian and Devonian, Laurentia, which is the supercontinent that North America was part of, collides with Baltica, Avalonia, and South America in succession. And this is going to form the antler arc off the western margin. We are going to start having orogenies, which is mountain building events. So we're going to start to see the ancestors of the Appalachian Mountains forming through these collisions. Whenever these pieces of continent come together, you're going to form a mountain, basically. So we are going to have the Akkadian orogeny in the late Devonian. Much of the United States would be submerged during this time. This yellow line here is the Paleo-Equator, so this is sitting close to the equator, so we're in a different climate zone than where we would be currently. So in the late Devonian, the Akkadian orogeny created a second pulse of Appalachian mountains that shed sediments onto the craton. This would form the Catskill Delta. The antler orogenic belt was uplifted on the west coast, so we start to form some of these coastal features that will eventually be part of the United States. And so, we're going to see that the land masses move throughout time. When I talk about plate tectonics, I will show you some reconstructions. And so these continents move quite a bit. We're talking about a long period of time. During the late Paleozoic, we're going to start seeing greater diversification of the life on land. It's going to get really big, and it's going to start looking somewhat like modern Earth. So during this time period, we are going to see new and abundant plant life. This plant life is important because it will become coal deposits that we still use today. So coal is organic material. So all of this new plant life, when it dies, it's going to decay and become resources. During this time, we're also going to see the formation of Pangaea, which is probably the most famous supercontinent. And we will see the worst mass extinction in geologic history, which will end the Paleozoic era. So the famous KT or KPG, Cretaceous Tertiary or Cretaceous Paleogene, is not the worst mass extinction. The end of the Permian is actually the worst mass extinction. So outside the US, we are actually going to see that if we look at this image, we see this thing called Carboniferous. That is the name for the period everywhere except the US. In the US, we split it into the Mississippian and the Pennsylvanian. Everyone else just calls it the Carboniferous. It's called the Carboniferous because this is where we see these large, massive land plants that will then become coal deposits. And so there's a lot of carbon available. And then again, we have a massive extinction at the end of the Permian. So the Carboniferous, or the Pennsylvanian and Mississippian, or Mississippian and Pennsylvanian rather, this is, we have these massive plants. Trees and ferns grew in extensive swamps, which when the organic material fell onto the surface, it then was able to eventually be turned into these coal deposits that we're still using today. The plant life was massive. So here's a museum diorama showing a Carboniferous coal swamp. There's a giant dragonfly which had a wingspan of about 1 meter. So this inset gives a sense of the size relative to a human. I would not want to run into this dragonfly. So at the end of the Paleozoic, almost all of the land had combined into a single supercontinent called Pangaea. We had the Alleghanian and Hercynian orogenies, a huge mountain belt formed during this time. So that's what we're seeing here. The Caledonian orogeny had formed earlier. We have coal swamps bordered interior seas, so we see these coal swamps. And the ancestral Rockies are starting to form at this time. So if you ever have traveled to the Appalachians, those mountains are much lower in elevation, and they're very rounded. They're much older than the Rockies, which is why they've been worn down a lot. They're not, once we left these time periods, they weren't constantly being uplifted. So they're a much older mountain range compared to the Rockies, which are a very young mountain range. So here we see Pangaea together. Most of the continents are part of Pangaea at this point. So we have a mass extinction at the end of the Permian, the first, or the largest mass extinction rather, in Earth's history. A mass extinction means that there's more loss of species diversity than gain. So in the orangish yellow, we have origination of genera, so we have new genus, and in purple we have extinction of genus. So we can see here that at the end of the Permian we have this very large extinction. We have a 70% change in the extinction of genus, but we're only seeing maybe like a 24% change in the origination of genus. So this is what we mean by mass extinction. It's such a large loss of species that we call it the Great Dying. So it's the first great mass extinction that affects the vertebrates on land. So the previous mass extinctions were primarily in the oceans. Now we actually have a large proportion of life on land. This one also did wipe out nearly all of the marine species, or taxa rather. So between 80 and 85% of all species alive on Earth at the end of the Paleozoic are wiped out in this mass extinction. 95% in the oceans and 70% on land. So the ultimate cause is thought to have been a massive volcanic eruption that produced what are called the Siberian traps about 250 million years ago. So here are the traps in Siberia. These are basically large outpourings, larger than a country. I mean, this is Siberia, which is lots of land, but this is larger than most countries, outpouring of volcanic material. This changes the surface of the planet, basically. Luckily, we don't have any modern examples of these type of volcanic outpourings. We will see them throughout history. Typically, when they happen, we see a lot of extinctions because it will change the land surface. So the Permian ends the Paleozoic, and then we move into the Mesozoic. So the Mesozoic is middle life. The Mesozoic is probably one of the more common eras that people know about because the Mesozoic is where we have the Triassic, Jurassic, and Cretaceous. So during this time, Pangea fully assembles or finishes assembling and disintegrates. We have the appearance of dinosaurs in the late Triassic. They have great diversification throughout the Mesozoic, and then they die off at the end of the Cretaceous. Mammals do start to arise in the Triassic, but they are very small and they are not the dominant species or dominant family on the planet. We do have flying reptiles and eventually birds appearing. We have some species are still around, like turtles, sharks. So we have a lot of diversification in life. I have to share this because I happen to like Jurassic Park a lot. I think it's it's some of the science is really bad, but I think it holds up as pretty good special effects at least, and I just think it's fun. This is just a fun comedic take on Jurassic Park, so hopefully this will work right.
Oh my God, Ellie!
They're magnificent.
My dear Dr. Grant, welcome to Devonian Park.
What are they doing?
Feeding them.
These sea stars are ruthless, alright? They can strip the plankton off that cow in as little as 7, even 6 days.
Oh, no.
What is that? Early single-cellular protista! Run! They may also possibly be early jellyfish! Scientists are undecided!
Go!
Whoa! The gastropod mollusk is on our tail!
This is what happens when you play God, John. These creatures don't belong in our time. Well, actually, turtles are evolutionarily very old. They belong in both our times. It's still a dangerous predator. Oh, it's on its back.
Nice trilobite. Good trilobite.
Oh no! Raptors!
Wait a minute, this is Jurassic Park. Velociraptors are from the late Cretaceous period, and they should be half the size, and covered in feathers. The only historically accurate dinosaur in this whole damn park is the T-Rex. And you're supposed to be a scavenger, not a predator.
Hi, I'm Zach from College Humor. Click here to...
Okay, I think that is humorous. I am not a paleontologist, but even I recognize that they are throwing together dinosaurs from all different periods in Jurassic Park, and I think they just liked the name Jurassic, which is why they picked Jurassic. So, but I do like to show that because I think it's funny. So in the Mesozoic, again, middle life, we have a large, after that massive die-off at the end of the Permian, we now have a new diversification of life in the seas. So trilobites are now extinct. They had been around for a long time. We now have a lot of bivalve mollusks are going to predominate, especially in the early Triassic. The ammonoids recovered, so they didn't completely go extinct at the end of the Permian. They are going to become important, what are called index fossils, which I will talk about next week. Belemnoids, which are a relative of the ammonoid that are squid-like, and sea urchins will start to diversify. So we see, these fossil records showing massive, colonies of these creatures in the sea. At the end of the Triassic, we had another extinction. So remember, I was saying it's a good thing we don't have any of these modern examples of these massive outpourings of volcanic material. Here's another example. So this happened in the central Atlantic. And so this is thought to have caused climate change. So we see that we have records that give us a indication of the proportional concentration of carbon dioxide in the air. And if we look at between the Triassic to the Jurassic, we see a massive increase in CO2, which is going to change our temperatures. It's going to increase our temperatures. So we're going to see that the temperature will increase between these two periods, and that can lead to an extinction. Throughout the Mesozoic, we are going to see that dinosaurs are going to rule the land. They will cover all of the niches, which means they will take every sort of evolutionary path they can. So there's a dinosaur for everything. They dominate the Earth throughout all of the Mesozoic. During the Cretaceous, which is the last period of the Mesozoic, we start to see these large plants. We need large plants to allow large animals. So massive flora allows massive fauna, because remember, a lot of these dinosaurs are very large animals. So here we have a Cretaceous fossil leaf from Greenland. It very closely resembles modern breadfruit plant from the tropics. This is something that is going to be able to support some of those massive creatures. So at the end of the Cretaceous period, if we look at where our land masses are, it's starting to look much like the modern world. We can start to see, we see the beginnings of most of our oceans. We're seeing that everything's starting to kind of move towards its present location. Antarctica and Australia are still together, but we start to see everything else is starting to kind of slide into their presence. And at the end of the Cretaceous, everything is bad. Everything goes bad at the end of the Cretaceous. Again, not as bad as the end of the Permian, but still everything goes bad. So there's strong evidence that indicates the Cretaceous was closed by a catastrophic impact of a meteorite about 13 kilometers across. This impact created a huge crater, and it created a tsunami about 2 kilometers high, which is really big for a tsunami, I might add, and set forests ablaze. The impact blasted so much debris into the atmosphere, which included sulfate aerosols from vaporized gypsum, that it ended up blotting out the sun and shutting down photosynthesis. So basically, everything shut down pretty instantaneously, too. So we call this Cretaceous Paleogene, or the old term is the Cretaceous Tertiary. So the KT, K is the abbreviation for Cretaceous. T would have been Tertiary. That's what these charts are actually showing. Paleogene is the modern term, so it's also called the KPG. So we see this one's showing percent extinction. We're seeing this massive percent extinction. This is the number of genera. We're seeing this drop in the number of genera. Again, we see these that match up with these changes between periods, and the Permian is the biggest one, but we see one at the end of the Ordovician. We see one at the end of the Devonian, end of the Permian, end of the Triassic, end of the Cretaceous. So these are common. So this boundary, the Cretaceous Paleogene, is characterized by an almost instantaneous global change in fossil assemblages. This was brought about by the sudden mass extinction of most species on Earth. The dinosaurs, which had been ruling the planet for 150 million years, vanished. 90% of plankton and 75% of plant species disappeared forever. The boundary is recorded in the rock record. There's also possible sites that show the die-off, but these sites are under some debate. But we can actually see this. You can go put your finger on this boundary in the geologic record. So I left in some of these questions. True or false? In a mass extinction event, all species go extinct. So is this true or is this false? Well, this is false, because if all species went extinct, then life would basically stop. So something has to survive. A mass extinction just means that there are more species going extinct than are coming into being or surviving. So at the end of the Cretaceous, we no longer have dinosaurs, we no longer have ammonoids, mosasaurs, and other marine reptiles. We have a reduction in our plant life as well. We have a massive die-off of the plankton. So the main cause for this is a meteor impact. So we see an iridium anomaly, which indicates a massive impact. We also see extinction patterns in, we have minerals from, this time period that are showing that they've been shocked. Here's an example where we can actually go stick our finger on this boundary in Canada. These are cooled molten droplets that are from this time period as well, which indicates that we had vaporized rock. So this happened at the Chelyabinsk impact site off the Yucatan Peninsula in Mexico. So the likely site of this impact is the Chelyabinsk crater. It lies beneath the northwest corner of the Yucatan Peninsula. It's buried, but it's 100 kilometers wide, visible through gravity surveys, which is what we see here. And as a subtle change in surface drainage and vegetation. So radiometric dating indicates this crater formed about 65 million years ago, which fits with the end of the Cretaceous. So 100 kilometer wide crater formed by a 13 kilometer wide impactor. So at the end of the Cretaceous, the dinosaurs are all gone, which means, oh wait, there's a big opening for basically the dominant life on Earth. And mammals are going to jump at that opportunity. So mammals first started in the Jurassic. They, diversified slightly during the Cretaceous. But once we hit into the Paleogene, wow, we're just going to go crazy. So now we are going to get absolutely crazy once we get into the Paleogene and then eventually into the Cenozoic. Well, no, I'm sorry. The Paleogene is the Cenozoic. So once we get into the Cenozoic, animals or mammals are just going to go crazy. Also, during this time, we're going to have angiosperms, which are flowering plants, will become the dominant plants on land. We're going to have grasses appearing in the Paleogene. So this plant life is going to be helping mammal life diversify. It's also going to help mammals become predominant. So another one of these questions left in, true or false. Grass is just a plant that grows in someone's backyard. So do you think it's true? Do you think it's false? And this is false. Grass is actually a distinction for a type of plant. So grasses are most of the grains that we use are actually classified as grasses. So the grass that grows in your backyard is actually not agricultural grass. So during the Paleogene, we start to have the ancestors of modern mammals. So here are examples of horses. So this is a Paleogene horse. It doesn't look very much like a modern horse. It's about the size of a small dog. It has multiple toes. Then we also have elephants. So here are some elephants. They ranged in sizes. So this one's about 1 meter tall. It has a very short snout, has multiple toes. This one's about 2 meters tall. It looks a little bit more like a modern elephant. So we do have all of these actually present in North America. We have fairly close to us Mastodon State Park, which is called that because of remains of mastodons. So these are things that were in America during the Paleogene. We also have some rather frightening. This is a giant bird, Diatryma. It's a flightless but powerful bird, but powerful beak and claws, so it's like a ostrich on steroids. 2.4 meters, about 8 feet tall. This is not something you want to run into. And it, is attacking in this illustration the ancestor of the horse. So one of these other questions I left in here, true or false, horses and their relatives have remained in North America since their ancestors first appeared. So do you think this is true? Do you think this is false? And this one's false. So the ancestors of the horses were in North America. They died off, as did, the ancestors of modern elephants also were North America and died off. Saber-toothed cats, all of these were in North America. They died off at the end of the last major ice age. Horses were reintroduced by European explorers, modern horses, to America, or to the New World. So they were brought over, during their exploration and then got loose. And so modern horses, there was a gap in time, and in North America where horses were not there. So during the Eocene, it was actually fairly warm during that period. So the Eocene was similar to a modern climate. Towards the end of the Eocene, we started to have glaciation. And then into the Oligocene, we had glaciation. So possible causes of this, separation of Australia from Antarctica, which would have then established a cold circumpolar current, which is basically allowing cold water to circulate around Antarctica, which then would lead to glaciation of Antarctica. We then form these ice caps, which can drop the temperature because, again, we didn't get a full snowball Earth, but once you start forming that ice, you're going to drop the overall temperature. So the Neogene, we have this massive fauna. We are going to have, this is an interesting, we've got Neogene fauna depicted by Neogene humans up here in the corner, and modern humans down here. I personally prefer the cave art, but we're seeing examples of, large mammals, predominantly mammals. They're large, they're adapted to this colder environment. And then the climate changes, and these animals that are adapted for these cold environments aren't going to survive very well. The Oligocene, which is 28 to 23 million years before present, is important because we're going to start to see the appearance of monkeys. This is a key aspect to modernization of animals in the Oligocene. Monkeys are important because they have a relatively large skull, so their brain is unusually large for an animal of their size. So if you compare similarly, animals of similar mass, they typically have, a certain fraction of their mass in their brain. Monkeys have a, higher amount of brain size to their body size than other animals, which is then going to allow them to start to develop, using tools. We see even now, modern apes, we see, and some monkeys, we actually see them using sticks to dig out termites, things like that. And then this is going to lead to some of our ancestors. So our immediate ancestors, rather, are the Australopithecines. They evolved 4 million years ago. The genus Homo, which is the grouping we fall under, appeared suddenly about 2.4 million years ago. So the Australopithecus is about 4 million years ago. There were hominids earlier than that, but we see the Australopithecus eventually evolving into the early Homo. Homo erectus was the first Homo genus or the first Homo species that walked upright. We have like Homo habilis, which were the first ones that used tools. Up here we see Homo neanderthalis and Homo sapiens. Homo sapiens are modern humans. Homo neanderthalis were related to modern humans, and there is some Neanderthal DNA still in modern humans, but they pretty much died out. All of this is happening in the Neogene. So 4 million years ago is in the Pliocene. 2 million years ago is in the Pleistocene, which was during Pleistocene we had an ice age. 300,000 years ago is when Homo sapiens first really came about. That's in the Holocene. Or I'm sorry, 300,000 years ago is when Homo sapiens, earliest Homo sapiens. The Holocene, which is the modern epoch, started 12,000 years ago. So humans have been around for just a small fraction of this. So quaternary is an old term, really. We don't use it very much anymore. Tertiary, is not used very much anymore either. So the Paleogene is broken into some of these other terms. So we were talking about the Paleogene, and then we just moved into the Eocene and the Oligocene. The Miocene and Pliocene are when we're starting to see these large animals that are from the Ice Age animals, and the Pleistocene is when we see the Ice Age becoming predominantly Ice Age, and then at the end of the Pleistocene we move into the Holocene, which is when we have our modern time. Again, the Holocene is about 12,000 years ago. And so there is no pre-lab video for this week. We have exam 1 this week, so we're not doing a pre-lab video. I will be discussing exam stuff during class, so I will see you this week in class. Please be studying. Good luck on everything, and I believe that is all for this lecture.